Hello, my name is Andrew Ng, and what I'd like to do today is talk about sparse autoencoders and unsupervised feature learning. So it turns out, I think unsupervised feature learning is a relatively new and I think very exciting area in machine learning that I think is addressing one of the major open unsolved problems in machine learning. And with this lecture, hopefully I'll get to tell you about some of that. Let's see, before I get started, I should say there are notes on the course website that accompany this lecture, and so as you listen to this lecture, feel free either to take notes as you're listening or to refer to the online lecture notes afterwards to get all the math and the details and so on. And finally, since this is a video, just also encourage you to, whenever I put up an equation, just encourage you to, feel free to pause the video and slowly read the equation, make sure you really understand it before you move on to the next part of the lecture. And so with that, let's get started. In outline, what we're going to do is first motivate the problem of unsupervised feature learning, and then having done that, we'll talk about one algorithm called neural networks, which it turns out will be a supervised learning algorithm. And following that, we'll show how to adapt the supervised learning neural network algorithm into an unsupervised learning algorithm called an autoencoder. Talk about how to incorporate ideas of sparsity into it, and then finally talk about ideas of visualization in order to figure out just what our algorithm has learned. Let's start by talking about unsupervised feature learning. So, if you think about how computer perception is done today, for example, computer vision object detection, if you want to write a program to, say, recognize staplers, what you do is you implement, some computer vision features that would, so you have an algorithm that takes as input an image and will compute, say, low-level computer vision features. And in this image, I've shown the results of an edge detection algorithm. And then there's these low-level vision features that you then feed to, say, a supervised learning algorithm that then tries to recognize objects. And, well, that's vision. How about audio? Well, we have tasks like speaker identification, where you're given an audio clip and you want to recognize the identity of the speaker. Then you sort of see, a fairly similar pipeline where your algorithm may take as input the raw audio signal, and then given the audio, you might compute relatively low-level audio features, in this case such as spectrogram, and then it's really these low-level audio features that you give to, say, a machine learning algorithm, a supervised learning algorithm, which then, say, recognizes the identity of the speaker, does speaker identification. And in many problems, this idea of coding up these low-level features, low-level vision features, low-level audio features, is I think, the significant challenge that takes a long time to do. And in fact, these are two examples from perception. It turns out that if you look even at applications in control, even then you see a fairly similar pipeline. So, some of you will know that some of the students over the years have worked a lot on helicopter control. And it turns out that one of the ways to control a helicopter is also, with a similar pipeline, where given a helicopter state, meaning helicopter position, say, you will need to code up low-level state features of the helicopter, and it's really these state features that you give to a machine learning algorithm that then learns a strategy for controlling a helicopter. And in sum, this sort of pipeline turns out to be very common, where you have sensor inputs and you need to compute low-level features, and there's these features that gives you the representation you feed to a learning algorithm or other AI algorithm that then does something. And I think a key question in a lot of machine learning, a lot of AI, is where do you get these low-level features from? So on the previous slides, I used the examples of for perception, I used the examples of computer vision and the example of audio understanding. So, let's look at computer vision and ask, in computer vision, what is the state of the art in coming up with low-level vision features? Well, the answer in computer vision is, over the last few decades, there have been teams of somewhere between tens and hundreds and thousands of engineers that have spent, years or decades, or essentially large fractions of their career, hand engineering features for computer vision. And even today, there's a lot of computer vision research on how to hand engineer better features. And what I've shown on the slide are just a few examples of vision features people have come up with. And I sort of don't want to criticize this work. A lot of these are very clever ideas, but you have to ask, is there something you can do better than spending years or decades sitting around hand engineering features? And even though some of the results of that hand engineering process are pretty clever. And you sort of have to ask, can we come up with better features in hand engineering? So that was vision. How about audio? Well, it turns out that the state-of-the-art feature design answer to audio is there are teams of somewhere between tens and hundreds and thousands of audio researchers around the world that spend decades and large fractions of their career sitting around hand engineering audio features. And again, some of these features are actually very clever, but once again, you have to ask, is this the most scalable approach to designing features for machine learning? And in fact, for those of you that work in other problems than vision and audio, right? Was this approach scalable? As one example, one thing I sometimes do is work in robotics, and on robotics problem, we don't just have camera and audio features. We actually have a plethora, a wide range of many different sensors, like camera arrays, even fun things like thermal infrared. It turns out that thermal infrared is actually a great sensor to use if you want to do people detection, because we as people we emit heat, and so we glow in thermal infrared images, as well as various 3D range scanners. And so if every time I buy a new sensor from a robot, if every time I buy a new sensor, I need to hire a team of somewhere between tens to hundreds of thousands of engineers and wait several decades for them to hand engineer features, that's just not scalable. And more broadly, for those of you that have done a lot of work in applied machine learning, you also found it time-consuming to design good feature representations. So I think one fascinating question is, can we come up with algorithms that can automatically learn good sensor representations? And in order to try to get at an answer to this question, I'm actually going to turn a little bit to biological inspiration. So, like many machine learning researchers, I tend to treat biological inspiration with great caution, but so I won't take this maybe too seriously, but I think there's some interesting elements to it, so let's take a look at that. So it turns out that there's some evidence that suggests that the human brain, say, can learn an amazingly diverse range of sensor representations for an amazingly diverse set of sensor modalities. So, for example, the picture on the upper left, this is actually a system, I think, undergoing FDA trials now called BrainPort, in which it turns out, even as adults, you and I today can still learn to see with our tongues. So the way it works is you take a camera and strap it to your forehead, facing forward, and what you do is you run a wire from the camera to an array of electrodes that you place on top of your tongue. And what the system does is it takes a grayscale image and it converts the pattern of pixel intensity values, the picture taken of what's in front of you, and it converts the matrix or the image of the grayscale image, the pixel intensity values, into different voltages that are then impressed on different points of your tongue. And I think it's pretty safe to assume that we did not evolve, right, learning to see by patterns of voltages on our tongues. But the amazing thing is, even as adults today, with a few hours training with a system like this, you can actually learn to see a little bit with a system, with your tongue. And with longer amounts of training, you can learn to see with greater and greater visual acuity. So that's the example on the upper left. On the upper right is the example of human echolocation or human sonar. So let's see, here's how that works. Imagine this is a blind person, right, and maybe with eyes totally destroyed. So it turns out that the people that have trained themselves to either snap their fingers or make clicking sounds with their tongue. So you can go, right, make clicking sounds with your tongue. And by interpreting how the sound bounces off the environment and comes back to your ears, there are actually people that can train themselves to interpret that as sonar, use human echolocation. And so, so if you want, you can actually, if you want, right, go around with your eyes closed, making clicking sounds with your tongue, and train yourself to walk around and not run into things. I don't know if you actually want to try it yourself. One last example shown on the bottom. So let's see, this has been done on, I think, at least 4 mammals now. But so the little red region shown in the image, right, that little red region on the brain is called the auditory cortex, and that's the part of your brain that's normally responsible for processing sound. So it turns out what you can do is do surgery on an animal. I think this was first done in ferrets, repeat on several other animals now, where you, let's see, so normally in the brain you have the ears feeding the auditory signal to the auditory cortex, and then the auditory cortex processes it, and that's how you hear. So it turns out you can do surgery to cut off this connection from the ear to the auditory cortex, speaking a little bit loosely, and rewire the brain so that your visual signal from your eyes now goes to the auditory cortex. And when you do this, speaking a little bit loosely, what you find is that the auditory cortex then learns to, quote, see, putting a little bit in quotes, but, and the amazing thing is that what this shows is that a part of your brain that's normally responsible for hearing can instead learn to process visual modality, right? So, there's this hope or hypothesis with no proof that, if the brain can do this, can learn to represent, can learn appropriate sensory representations ranging from patterns of electricity on your tongue to sonar to, using the same piece of brain tissue to either learn to hear or learn to see in the case of the auditory cortex. Is it possible for us to come up with an algorithm, with a machine learning algorithm, to do something similar? To come up with a machine learning algorithm that can take some sense of modality and just learn an appropriate representation for it, which is maybe what maybe the brain seems to be doing as well. And so concretely, here's the problem I want to pose. Rather than demanding that you have teams of people engineer features for you, is it possible to have an algorithm and just show your algorithm lots of images and have an algorithm that can automatically learn or ultimately find a better way to represent images than the raw pixels? Okay. And you can, and if you have a robot, you can imagine doing this by sending a robot to just wander around and take lots of pictures, or even for your computer, you can also just suck down images off the internet. And the question is, can you learn a better representation? For example, just as I showed, one specific image earlier, the result of doing edge detection on a stapler image I had, is it possible for an algorithm to just look at images like these and, quote, invent edge detection by itself, or maybe invent other features as well? And if you can do this with images, well, I guess the challenge is really to come up with an algorithm that can do this. So rather than, so equally exciting would be the question of whether you can apply this idea to other sensor modalities as well. So, for example, rather than hand engineering features for audio, can you show a computer or give a computer access to tons of audio and have it learn a better representation for audio? And if you have algorithms like that, then maybe you can even give the computer sensor representations or other data that may not correspond to the natural human senses, things like vision and audio. But for instance, 3D range scans is not a natural human sense, and so I think our human intuition for 3D range scans is often much weaker than our intuition for vision and audio, and that makes it harder, I think, for us to hand engineer features for it too. But if you can just give a computer tons of unlabeled data for 3D range scans or audio or images, can you get it to automatically learn better representations for all of these? So that outlines the problem of unsupervised feature learning. And what I'm going to do is talk about an algorithm called neural networks, which will eventually lead us to an unsupervised feature learning algorithm. Turns out that as we develop our neural network, we're going to first develop a supervised learning algorithm, and then we're going to modify it to become an unsupervised learning algorithm. So, with that, let's get started on our description of neural networks. Now, our application of neural networks is going to first be to a supervised learning problem, and so we're going to assume we have training examples xi, yi. Right? So label training examples where x is the input features and yi's are the output or the target labels. And for those of you that have taken a class with me like cs221 or cs229, this is the same notation as I'm using for there. And so the way we're going to develop a neural network is we're going to first define a hypothesis class, meaning first define a specific class of functions. So we define a hypothesis class, which I'm going to write h subscript wb of x, where here the parameters of the hypothesis class are w and p, and then given a training set with our labeled examples, we're going to fit the parameters w and b to our training set. So let's see. In order to lead up to our discussion on neural networks, I'm actually going to start with a much simpler model which corresponds roughly to a single quote neuron. And neural networks make a loose analogy to neuroscience and neurons in the brain. It's called this a very rough model of a single neuron. And what I'm going to do is draw a little picture like this to denote the computation of a single quote neuron. And so let's see, in this picture, this quote neuron takes as input three features, x1, x2, x3, and it also takes as input a biased term which I've written as +1. And what it does is it performs a computation that turns out is very similar to the computation that logistic regression does, for those of you familiar with logistic regression, okay? With some changes. And so concretely, what this neuron outputs is a function, this hypothesis h subscript w comma b of x is equal to a function f, which I'm going to call an activation function, applied to w transpose x plus b. And just write that out, that's equal to f of sum from I equals 1 to 3 wixi plus b. Okay? Where w is a vector in this example and b is a prime number. So the function f is called the activation function. And for those of you familiar with logistic regression, so let's see, there are different choices we can make for the activation function f. And so if you were to choose f equals 1 over 1 plus, oops, if you were to choose f of z equals 1 over 1 plus e to the minus z, that's called the sigmoid function. Right? If that's your choice for f, then this unit here becomes a lot like, really, essentially a logistic regression algorithm. What I'm going to do in this lecture is actually choose a slightly different activation function. And in particular, I'm going to choose f of z equals the tanh function. Tanh also is an abbreviation for the hyperbolic tangent function. And that's defined as e to the z minus e to the negative z over e to the z plus e to the minus z. And just draw out what the tanh function looks like. So that's what the activation function f of z or tanh of z looks like, with z on the x-axis and the value of f or tanh on the vertical axis. And so the tanh function takes values between +1 and -1, And this is basically a rescaled version of the sigmoid function. It's actually rescaled on both the horizontal and the vertical axes. But you can think of this as a version of the sigmoid function where the outputs range between -1 and +1 instead of between 0 and 1. Okay? And so you can choose different activation functions, but for the rest of this lecture, I'm going to assume that we're using the tanh or the hyperbolic tangent activation function. So, armed with that definition of an activation function f, this little picture here now gives us, I'm going to use this little picture shown on the upper left to denote a single, quote, neuron, okay, which basically applies an affine or linear or affine function to the inputs and sends it through this nonlinearity. So, and many of your intuitions for logistic regression will also apply to this tanh activation function here on this one. Now, what we're going to do is then take a bunch of these neurons and put them together, and that's what will give us a neural network. And so let me go ahead and draw an example of a neural network. So here are my inputs, x1, x2, x3. I'm going to draw the +1 same as before. And to draw a neural network, I'm just going to put circles around all of these nodes as well. So we're going to call these our input neurons. And then here are a set of additional neurons, with this one at the bottom being another +1 neuron. And we're now going to draw arrows connecting the neurons in one layer to the neurons in the next layer. And then what each of these neurons does, what each of these 3 neurons in this middle column does, is it applies an affine function to the inputs and sends them through a nonlinearity. And what each of these 3 empty circles does is it then sends its outputs on, perhaps to other neurons, like this one over here on the right. And this neuron on the right maybe outputs the final value of our hypothesis. Okay? So, let's see. To introduce a little bit of terminology, these +1 units, right, those don't have inputs, and I'm going to call them bias units. And they basically correspond to the intercept term or to the offset term in our in each of our quote neurons. And this particular neural network that I've drawn is a 3-layer neural network, and I'm going to call the 3 layers, layer L1, layer L2, and layer L3 in this example, where L1 is also called the input layer. L3 is called the output layer, right, because it represents the final computation of the final output of a hypothesis H. And L2 in the middle, maybe not a great name, but L2 in the middle is called the hidden layer. And the hidden layer is just any set of layers in the network where the values computed aren't directly observed in the training set, right? So in our training set, we get to observe the inputs X and the target outputs Y, whereas these are intermediate values of the computation that are sort of hidden from us or not shown to us in the training set. And so maybe not a great name, but we're going to call them the hidden layer. Let's see. A little bit more notation. This neural network has a certain set of parameters. Let me just go ahead and quickly define the parameters here. Well, as you're listening to this lecture, I encourage you to not worry too much about the specific indices or the indexing of the parameters, and instead, hopefully the examples I go through will just make sense, and you can also go to the lecture notes afterwards to get the details of exactly what each of the parameters is and what the convention for the indexing of parameters is. Okay, so just don't worry too much about the indexing like this. But let's see, parameters of the network. It's going to be a set of parameters W and B, and I'm going to use the notation W superscript L subscript ij to denote the weight associated with the connection between neuron or unit J in layer L and unit I in layer L plus 1. Okay, so my neural network has 3 layers, and each of these arrows really is associated with a parameter, and so each of these arrows really is associated with a parameter, and so what W superscript L subscript ij does is it specifies the strength of the connection, or really the weight that unit I in layer L plus 1, right, applies or multiplies into for the input that corresponds to unit J's output in layer L. Okay, and again, don't worry too much if the indexing is a bit confusing. When I on the next slide, as I actually draw some of the implications, hopefully it'll make more sense then. And just the other parameter, just defining it for completeness, is B superscript L subscript I, and that's the parameter, or that's the bias associated with unit I. By unit, I really mean neuron, right? So neuron number I in their opposite. Okay, so these are parameters. And finally, let's define one more piece of notation, which is that, let's see, I'm going to use the notation actually, let me actually switch to a cleaner drawing of this neural network. Okay, so here's a cleaner drawing of this neural network, same as the previous slide. The last piece of notation I want to define is I'm going to use A superscript L subscript I to denote the activation, and by activation, that's synonymous for output value of unit I in layer L. So for instance, let's see where my mouse pointer is, or where my pen is. This is layer L2, the hidden layer of the neural network. And so if I call this, unit, hidden unit 1, hidden unit 2, hidden unit 3, then the output of this unit, of hidden unit 1 in the neural network, is going to be called A superscript 2 subscript I, right? Because that's, A superscript 2 subscript I is the activation, or really the output of the first unit in layer 2, which is the hidden layer. And similarly, here, A superscript 2 subscript 2 is the activation, meaning the output value of this second hidden unit in my in the hidden layer of my neural network. Okay, and similarly, the final output of my neural network, this we can also write as A superscript 3 subscript 1, because this is the first unit of layer 3 of my neural network. All right. That was the law notation. And let me now just write down a couple of equations that hopefully tie all this together and maybe make all of the indexing make sense as well. Which is, let me take this neural network and draw a slightly smaller version of it to give myself more space. And now let me just write down, the full computation that is that is reflected by the neural network picture shown on the upper left. Okay, so assuming that you have all the parameters of this neural network, then let me write down what the final output of the neural network h subscript w comma b of x will be, given a certain input. So let me write down the computation reflected by the network. So let's see, a superscript 2 subscript 1, that's the activation or the output of this first neuron up here, right? This is the hidden neuron 1. And that is going to be equal to f of w11, x1. Let's just write this down. Okay. So the output value of this first hidden unit is going to be, right, my activation function f applied to a affine or linear or affine function of the input x, right? Again, the term affine means essentially the same thing as a linear function, except that you're allowed to have also a non-zero offset term here. Okay? So if there were no b here, if there were only the first three terms here, it would just be linear function, or f applied to linear function, but because of this b here, this is called an affine function. But so this is what the first hidden unit in my neural network outputs is the tanh function applied to this function of the input. And what the second hidden unit, right, number 2 over there, does is it performs the following computation, where and similarly, excuse me. And similarly, the third hidden unit does a similar computation. Okay? So that's what these three hidden units do. And what they do is then send their output values to this final rightmost neuron in that then computes the final output of the neural network. And so what that unit does is it outputs this A31, which is going to be the tanh activation function applied to this. So this formula gives the final output of the neural network. Okay, and so this final, output neuron, this final neuron in the output layer is just another of our quote neurons that takes three inputs. In this case, is the A1, A2, A3 in this case, applies an affine function to that, and outputs that as the final output, applies an affine function to that, passes that through our tanh sigmoid-like nonlinearity, and then that's the final output of the neural network. And once again, don't worry too much about the indexing I'm using. I am using hopefully a consistent notation in the equations I'm writing down up here, but so long as you get the intuition behind the computation that is embodied by this picture on the upper left, that's really all you need to get for now. And when you implement this, do refer to the lecture notes, which sort of really, lays out the notation carefully and suggests exactly how to implement it. All right, so I point out one more thing, which is that if you imagine implementing a neural network to do this computation, it seems like one way to do this would be to use a lot of for loops, right? So you have a for loop that says compute A21 for the first neuron, then compute the activation of the second neuron, then compute the activation of the third neuron, and so on. It seems like they have all these sums which you implement with for loops and so on. It turns out that instead of having a lot of for loops, it turns out that a lot of these computations can be summarized into just a few equations using a very succinct matrix vector notation. And in particular, if you take all these equations, it turns out you can compress them into just essentially a few matrix multiplications or a few matrix vector operations. And by doing that, you can actually get a very efficient implementation of all of these computations of a neural network using, essentially fast linear algebra or matrix vector libraries. So I'm not going to do that in this video lecture, but you can get the details of how to do that as well from the lecture notes. Okay. So just one more thing I want to point out, which is that if you look at this picture of a neural network, remember I started off talking about the problem of feature learning, right? And so if I take this neural network and if I cover up the leftmost portion of it, right, like that, then if you just look at the rightmost portions of it, then what you see here is the output of the neural network looks a lot like taking a logistic regression unit. Again, this is a tanh activation function, very similar to logistic regression, but it looks a lot like taking the values A1, A2, A3 and passing them to logistic regression, right, with outputs between -1 and +1 rather than 0. So one way to think of this neural network is that if you imagine trying to apply an algorithm like logistic regression to your supervised learning problem, one way to think of your neural network is that this is saying, instead of feeding your raw features x1, x2, x3 to your logistic regression learning algorithm, what we're going to do is come up with a different representation given by these activation values A1, A2, A3, and instead we're going to feed A1, A2, A3 as our representation to our final, quote, logistic regression unit, and is that then outputs the final value of our hypothesis. Okay? So you think of the neural network as learning an alternative and hopefully better representation for the data, namely these 3 activation values, rather than the original inputs. And so this is sort of an algorithm that can sort of try to learn its own feature representations. And in fact, and of course for now, this is a supervised learning algorithm still that learns from labeled data, and later on we'll talk about how to make this an unsupervised feature learning algorithm. So far, we've been using this example as our running example of a neural network. It turns out that by drawing different patterns of connectivity, we can get different neural network architectures. And by different neural network architectures, I mean informally just different patterns of connectivity. And so, whereas this neural network has only one hidden layer, you can have neural networks with multiple hidden layers. And more interestingly, or perhaps equally important, you can also have neural networks with multiple output units. So let me show you an example of that. So by using a different pattern of connectivity, here's a different neural network that you can get, where again this leftmost layer is our input layer, and now layers L2 and L3, both of these are hidden layers. So this is a network with 2 hidden layers, and layer L4 here, our final layer, is our output layer, and this neural network actually has 2 output units, and so it is outputting values H subscript W B of x that are in R2. Okay, and so in order to train this neural network, you would need to have training examples xi comma yi, where the values you're trying to predict, yi, are also going to be in R2. And as an example of where of an application where you might do this, where you might have multiple output values, imagine, for instance, if you have a medical diagnosis application where x1 may be features of the patient, right, of a medical patient, if this is a medical diagnosis application, and if yi1 is whether or not they have disease 1, and if yi2 is whether or not they have disease 2. Okay? And so more generally, if patients come into your medical office and if they can have any one of k different diseases, or they can have even multiple combinations of different subsets of k different diseases, then you can build a neural network with k different output units, where each of these units would try to predict whether or not the patient does or does not have that disease. Okay. Now, taking some of where we are, we've defined, by drawing down a neural network architecture, we've defined a specific hypothesis class H subscript W comma B of x that, given an input x, outputs its prediction or vector predictions. And the parameters of this algorithm are these parameters W and B. And what I'd like to do next is talk about an algorithm for finding good values of these parameters W and B. And what I'm going to do is actually talk about these parameters or training a neural network in the online learning setting. And so to explain that, just so by way of contrast, many of you will be familiar with the setting of supervised learning in which you have a fixed training set, right? So for those of you that took cs221 or cs229 with me, for much of those two classes, we talked about supervised learning, where you have a fixed set of m examples, x1, y2, x1, y1, x2, y2, up to say xm, ym, if you have m training examples. In this lecture, I'm going to take a different view of learning, which is sometimes called the online learning view. And instead of having a fixed training set, I'm going to imagine that we have an unending sequence of examples. So we're going to imagine the learning algorithm, first see some example x1, y1, and then after that we get to show our algorithm x2, y2, and then after that we get to show our algorithm x3, y3, and this sequence just goes on and on, doesn't it? Okay? So in order to implement this, if you have only, if you're training a neural network and if you have only a finite training set, if you only have m examples, then what you do is you would actually revisit these examples in terms. You first, show your algorithm, show your algorithm x1, y1, then show x2, y2, show x3, y3, and so on until you get up to xm, ym. And then you would cycle back to the beginning, show x1, y1 again, then show x2, y2 for the second time, and so on. And so by going through this sequence multiple times, you can simulate getting an infinite sequence of training examples. But in fact, for some applications, it's actually not unreasonable to act as though, it's actually not unreasonable to develop algorithms for which you can actually just keep on getting more and more and more training examples. Okay? And it turns out that some of our algorithms will just be easier to describe using this online learning formalism. So our main algorithm for training the neural network will be an algorithm called backpropagation, which does stochastic gradient descent. And in the online learning setting, the way that proceeds is we're going to iterate for I equals 1, 2, 3, and so on. We're going to get the next training example. So xi, yi. And then we're going to do one step of gradient descent. So we're going to update w superscript L, jk for all layers L and for all indices jk. Right, that gets updated as w, L, jk minus the learning rate alpha times the partial derivative with respect to the parameter of some cost function j. Okay. And similarly, we also update the parameter, b, j, l gets updated as b, j, l minus alpha times, similar partial derivative, right, that hopefully you'll be familiar with. So this term will be the partial derivative of the cost function j with respect to this parameter. So it's just stochastic gradient descent. And because it's the online learning setting, we do this with our unending sequence of training examples. You just keep getting the next example, then the next example, then the next example, and so on. And alpha here is a learning rate parameter, and j over here is our cost function. And what you notice that in this formulation, our cost function is defined with respect to a single training example at a time. So I've written j of cost of the parameters w comma b is defined with respect to a single training example xi comma yi. Okay? And so what we're going to do is we're going to get one training example and then take a little gradient step using our cost function applied to basically just that one training example, there's one step of stochastic gradient descent, and we keep going. Then we get the next training example, and then again look at our cost function applied to just that one training example, and take a little stochastic gradient descent step, and we keep doing this until the algorithm hopefully converges. So what I'd like to do now is write out a specific cost function j of w comma b and xy on the next slide. So let's see. The cost function we're going to use for training a neural network, right? I'm going to choose the following cost function, right? 1/2 squared. So this cost function has two terms. The first term is a sort of a squared error term, right? And it measures the squared error in the predicted value on the parameters w comma b on the input x. So it measures the squared error between our predicted output and the actual observed label y. And just notice that in this definition of the squared error, this definition also applies when your target labels y are vectors, right? So h is a vector like the two-dimensional vector in the medical diagnosis example, and if y is also in R2, then this is the L2 norm, the sum squared differences between the components of these. So we're going to use the squared error term and try to minimize, take a little stochastic gradient descent step to try to reduce the squared error between the predicted value and the actual observed value. The second term here is called a weight decay term. And you notice that, let's see, we're doing gradient descent, so we're going to try to minimize, the sum of these two terms. What the weight decay term is a squared error penalty on the norm, a squared error penalty on the value of the parameters w. Okay? And so as you try to minimize this cost function, you're going to try to minimize the square value of your weights. And so what this weight decay term does is it tends to drive the value of the weights, somewhat towards 0. And by causing the weights of the neural network to become smaller, what the weight decay term does is it helps to prevent overfitting by basically reducing the magnitude of the weights. By convention, weight decay is applied only to these terms, only to these parameters w, and not to the bias terms, b, l, such to I. So we usually don't apply weight decay to these bias offset terms. Although it turns out that even if you were to do so, in practice it only makes a small difference to your results. And just to wrap up this description, let me just say lambda, right, this term up here, is, I'm going to call that my weight decay parameter. And what lambda does is it controls the trade-off between the two goals of minimizing squared error versus this weight decay term of the second goal of trying to keep the magnitude of the weight small. And so, if the examples are drawn if in this online setting, if you think of the training examples as being drawn IID or identically and independently distributed from some distribution, from some power distribution over examples, I'm going to write as script D, then you can think of stochastic gradient descent as trying to minimize, with respect to the parameters w and b, the expected value of xy drawn from D of j of w, b, semicolon, xy. Okay? So think of stochastic gradient descent as minimizing the expected value, as trying to minimize the expected value of this cost function, where the expectation is with respect to the training example is drawn from the distribution script. Okay. All right. So, in order to complete our description of the algorithm, there are just two more things we need to do. The first is, in order to run stochastic gradient descent, you need a way to initialize your weights, to initialize your parameters, right? So you need to pick an initial value for your parameters W and B, and then you can run stochastic gradient descent from the initial setting of the parameters. So it turns out for some learning algorithms, it's okay to initialize all your parameters to 0, but it turns out that for a neural network, it's not okay to initialize all your parameters to 0. And in particular, instead of initializing all the parameters to 0, what we usually do is, take the weights and initialize this W superscript L subscript ij, and initialize each of the weights randomly. For instance, according to a Gaussian distribution with mean 0 and variance epsilon for some very small epsilon, for instance. Lots of things will work. This is just one example. You can also initialize the weights to be from a uniform distribution around some small interval close to 0. Usually initialize the weights to be values, maybe not too far from 0, but to initialize each weight value randomly. And you do not initialize all the weights, not all WLij equals 0. Okay. And the reason for this is that if you were to initialize all the weights, if you were to initialize all of the weights to be equal to 0, then it turns out that, let's see, at iteration 0 of the algorithm, all your weights will be identical. It turns out that after you show the algorithm one example, and it does one iteration of gradient descent, it turns out that because all the hidden units started off computing the same function of the input, it turns out that if you work out the gradient descent calculation, it turns out that all the hidden units weights will be updated in exactly the same way. And so all the hidden units after one iteration will still have identical weights to each other. And then after the second iteration, the same thing still holds true, and after the third iteration, the same thing still holds true. But basically, if you initialize all the weights equal to 0, then all the hidden units will always be computing exactly the same function of the input. Or more formally, to use the notation we had, you find that A21 will be equal to A22 equals A23, and so on. And so on any input, every one of your hidden units will be computing exactly the same function of the input. I hope that sort of made sense. Don't worry too much about it if it didn't. But another way of saying why we need to initialize the weights randomly is we also call this symmetry breaking, where we initialize the weights randomly just to make sure that the different hidden units actually pick up on different aspects of the input. Okay. Let's see. So we initialize these weights W, to 0 to random values. The bias values B subscript L subscript I. These can be initialized to 0 or randomly. Usually doesn't make a huge difference either way. Okay. So that's parameter initialization, and having initialized the algorithm, the last thing we need to do is talk about how we're going to implement stochastic gradient descent. And so the way we're going to implement gradient descent, stochastic gradient descent, is with an algorithm called backpropagation. And what backpropagation is essentially an algorithm for efficiently computing all the derivatives you need in order to carry out the step of gradient descent. So let's see. Here's the intuition behind backpropagation. What we're going to do is for each node, or really for node I in layer L, right, we're going to compute a term that we'll call delta superscript L subscript I that measures how responsible that node is for any errors in the output. Okay? And then having computed these terms delta superscript L subscript I, that measures how responsible a node is for any errors in our network's output, we're going to be able to use these terms to, fairly quickly compute the derivatives we want. And so, in order to compute these, responsibility terms, these delta terms, we're going to do, there's sort of two cases, I guess. For an output node, right? Let's see, in layer. So I'm going to use n subscript L to denote the number of layers in my network, and so n subscript L is going to be my final layer, which is my output layer. So for an output node, I'm going to compute my responsibility term, right, as a function of the output and the target value. Okay, so for an output node, meaning a node on the rightmost of the final layer, I actually get to observe what the correct value y should be, right? And so I'm going to compute delta, as essentially a function of really how large my error is in terms of predicting y. Now, for a hidden unit, right? So for hidden units, or for other nodes where I do not get to observe the output directly, what I'm going to do is compute these responsibility terms. Let me write down part of the formula, and we'll see if this makes sense. Delta j plus 1, and then times some other things, I'm going to ignore that. Okay, so I'm going to say that for a node I in layer L, the degree to which I'm going to hold this node responsible for the errors in my predictions is going to be a weighted average, or a weighted sum of the degrees to which nodes in the next layer, right, this is delta subscript j superscript L plus 1, is going to be the degree to which node j is responsible for the errors in my neural network prediction. So the responsibility of node I in layer L is going to be a weighted average of the responsibilities of nodes in my in the next layer in the neural network, and it turns out that the weights in the sum are exactly the weights of my network. Okay. And so, just to maybe say a little bit more intuition behind that, given a network like this, for the output nodes like these two on the right, I can compute delta, I guess this would be layer 4, right, delta in layer 4 subscript I directly, because in my when I get a training example, I get a training example xi, yi, and so I can measure the output, the error of the output nodes directly, and then compute the responsibility terms for these nodes as a function of yi, and as a function of what my network actually output. Okay? Having computed these responsibility terms for these two nodes, what I can do is backpropagate them to compute responsibility terms for the nodes in my previous hidden layers. So it's going to be my delta in layer 3 for my different nodes I, and the responsibility of this node, right, is going to be a weighted average of the responsibility of this node and this node, and similarly for this one. Okay. Having computed the quote responsibility terms for the nodes in my third layer, I can then again backpropagate the responsibilities, down to my second layer and compute these delta terms for my other hidden layer, and so on. And it turns out I actually don't need to compute responsibility terms for my input layer. All right. That was the intuition behind the algorithm. Let me actually write out the algorithm in full now. So first, let's see. So backpropagation, starts running when I get a training example x comma y. And so what I'm going to do is first do what's called a feed-forward pass. The feed-forward pass just means write this out, to compute the activations of all units or all neurons in my network. And so feed-forward pass just means a pass from the left to the right, from the input layer, to the first layer, to the second layer, to the output layer, from layer L1 to L2 to L3 to L4. Okay? So having done that, I'm going to compute the responsibility terms for my output layer. So for each unit, or for each node in the output layer, and again, I'm going to use n subscript L, right, to denote the index of my output layer. So this would be 4 in the example on the previous slide. I'm going to compute delta NL equals that. Okay, so basically it needs to be the error in my output. So y was the target value, right? Again, my training example, the index I of y minus the actual value that was output by my neural network times this f prime derivative of f term. And eventually we're going to do gradient descent, so it's maybe not surprising that we have derivative terms somewhere. So this is going to be my, this is, actually, excuse me, let's write that better. This is, right, there's f prime over there, the derivative of f. Okay? So that computes the delta terms for my output layer. And now I'm going to do this for each of my other layers. For each layer, L equals NL minus 1, NL minus 2, NL minus 3, and so on down to layer 2. And I'm actually going to do this only down to layer 2. You can also do this down to layer 1, but we don't need to. Turns out you don't need to compute responsibility terms for the input layer because the inputs are what they are. They're sort of, you can't really change them. And for each of those, we're going to compute delta IL to be equal to that weighted average sort of term you saw on the previous slide times this delta, the responsibility term for the next layer, layer L plus 1, and then times the derivative term. Okay. And having done this, you would then back propagate these error terms all the way down to layer 2, which is the first hidden layer in your neural network. And having done this, the final step of the algorithm, which write down on the new slide, is we're going to update the parameters. And I'll just write down the formulas here for completeness, but I'm going to update these parameters as follows. And so you can now compute all of these terms efficiently now that you've computed all the deltas, all the responsibility terms. Okay, where once again alpha is a learning rate parameter, and you do this for all values of L and all values of I and all values of J. And it turns out that I haven't proved it in this lecture, but it turns out you can prove that when you implement the algorithm as I've described it here, what you get is exactly the backpropagation algorithm. What you get is exactly stochastic gradient descent. So these updates to the parameters correspond exactly to taking one stochastic gradient descent step on the cost function J. Okay? So that's the backpropagation algorithm, and by doing this you can implement a neural network and train it on the training set. So let's see. Just want to say a couple more comments about the backpropagation algorithm, which is that, once again, in the way that I've described this algorithm so far, I've been writing out a bunch of indices and so on, and it turns out that with backpropagation as well and gradient descent, you can also write a lot of this notation much more compactly using matrix vector notation and using matrix vector operations. And so I'm going to leave you to look at the lecture notes for the details of that. But if you're implementing backpropagation, both the feed-forward paths and the backpropagation and the updating the weights, it turns out that you can sometimes get a much more efficient implementation by using these matrix conventions, because you can use efficient linear algebra libraries to do all of these operations. So that's the first comment. Second comment is that it turns out backpropagation is one of the algorithms that's unfortunately notoriously difficult to get right. And it's a mildly complicated algorithm. And one of the unfortunate things about backpropagation is that it is sort of famous for, it's possible for you to implement a buggy implementation of backprop and run it, and often it'll actually look like it's doing something reasonable. So it turns out, for instance, that if you were to forget to update the bias terms, just forget, if you were to, forget to include bias units in your neural network, usually your neural network won't do as well, but often it'll actually learn something that sort of looks okay, right? And I've all seen sort of bizarre bugs in neural networks where, for instance, you may have an n-layer neural network, and you maybe because of an off-by-one indexing error, maybe you're training all the weights except for the weights that connect the input layer and the first hidden layer. And even with a serious bug like that, often it turns out the neural network will actually learn something reasonable. So it is entirely possible to have a buggy implementation of backprop and still have it, look like it's learning and look like it's doing something reasonable. But unfortunately, the buggy implementations will usually just not do as well as a correct implementation. But it can be hard to tell, right? You may actually not even realize that you're running a buggy implementation because it looks like it's learning. So let's see. This is a tough problem. There are maybe two suggestions for that. The first one, which is what I often do whenever I implement backprop, is having implemented backprop, just do check your code carefully and do sort of read over your code carefully and carefully, re-examine every line and see if it's really correct, and just read over your code several times. I tend to do that whenever I implement backprop. One thing that quite a lot of people do that you might consider doing, some people do this, some people don't, is to numerically check your computation of the derivatives as well. And so, if you know how to do that, if you know how to numerically double check derivatives, then some people will do that too, to try to ensure that they have a correct implementation of backprop. Okay? And so, that's it for neural networks as a supervised learning algorithm. And based on what you know now, you should be able to take a neural network and take a training set and apply it to a supervised learning problem and hopefully get some reasonable performance. Okay, so we've been going on for quite some time now, and for those of you that want to take a break or get yourself a glass of water, now would be a great time to do that before we come back and do the second part. There's actually lots more I want to say about neural networks and how to turn it into an unsupervised learning algorithm and get to sparse autoencoders. But this is now a great time to take a break before we come back. And for those of you that are watching it with your friends or watching in the group, this would also be a great time to turn to each other and check if all of you understood everything and talk over points that you might want to clarify or make sure you fully understand. So do that and take a break, and when you're ready, we'll come back and do the second part of this lecture on taking neural networks and developing